Okay, hello everyone. In this video what I want to do is spend 5 minutes motivating sections 1.3 and 1.4, which cover limits and continuous functions. And I'm going to do this all in about 5 minutes, and I wanted to do these two sections together because they're very much interrelated. So those are over limits and continuous functions. And so why should we study limits? Well, I first want to say that limits are an important mathematical concept. They report the behavior of a function leading up to and following an instant in time, or leading up to and following an x value, and they ignore the actual value of the function. And it's that's important to ignore the value at that function because it reports something about behavior and not about values. And so I'll explain that in a second here. But I just wanted to point that this is like an important concept throughout calculus, is that you're reporting behavior leading up to and leading up to points from the left and right, and that's just key in all of calculus. So I'm going to say that they are key in defining continuous functions, which we will do in this section, but they're also the key component to differentiation, which is half of calculus. This picture right here is demonstrating what differentiation is doing. Is it's taking some curvy function and it's reporting the behavior near a point, and what you get is this, what we call a tangent line or a velocity vector or something. It's a line that explains the behavior near a point of interest. That's half of calculus. We're going to spend about 2/3 of this class doing that sort of thing. And then the other half of calculus, which is taught at the end of this section and also in Calc 2, is integration, which is summing up areas under a curve. And so that also involves the limit as a key component of that definition. So essentially limits are important to all of calculus. The first half, which we spend a lot of time in this class doing, and the second half, which we'll spend a little time in this class doing, but if you go on to take Calc 2, you would spend a lot more time doing that. Okay, so what is a limit notation? Well, like I said, a limit is reporting behavior. So to give you a good example, pretend that my mouse is Mario running along a path in a video game, right? So if you can make that imagination, then what the limit function is going to do is it's going to report the behavior or the height of Mario as he approaches a given point and then as he leaves a given point. Okay, so this notation right here, if I read it to you, says find the limit as x approaches -1 from the left. So that superscript -1 is saying take the values just to the left of -1. So as x is approaching -1, what is Mario's height doing? Well, he's running up this hill and he's running towards the y value, y equals 1. And you can almost see this as like he ran to the y value 1, jumped to 1.6, dropped back down, and then ran down the hill. Well, the limit as x approaches 1 from the left is just reporting on the values as x gets really close to -1 from the left, and it's saying that the values are going towards y equals 1. Okay, that's the limit from the left. The limit from the right is limit as x approaches -1 from the right of f of x, and that's saying that if Mario was running backwards towards 1 from the right, his height would be getting closer and closer and closer to 1. Okay? That's the limit from the right. And since those two limits agreed, the left-hand limit equaled the right-hand limit, and they both equaled 1, we'd say that the limit exists and it equals 1. And notice that it ignores the fact that f of -1 is actually defined to be 1.6. Okay, so Mario's height there was actually 1.6. That doesn't matter. It's only picking up on the values close to and just to the left of -1 and just to the right of -1. If you want another example, you could go over here and see that there's a little hole here, so the function is actually not even defined there. But Mario's height would be getting closer to -1 from the left and -1 from the right, so the limit we'd say that the limit as x approaches -3 is y equals -1. Okay, one more example of the same graph. If you move over here to 1, you see that Mario would be running along this curve, and then his height would be getting closer and closer and closer to -1 as x approaches 1 from the left. And then if you were running down this hill from approaching 1 from the right, his height would be getting closer and closer and closer to 0. And since the left-hand limit does not equal the right-hand limit, in this case we say that the limit does not exist at x equals 1 because we have this jump. Okay, so limits are picking up on jumps. They're ignoring holes. Okay, if there's a big jump like this, limits pick up on it. If there's a hole, limits ignore that. Okay, so that's what a limit is, and like I said, it's going to be very much important in defining continuous functions. And so then I asked, well, why do you study continuous functions? Well, continuous functions are the functions that you can throw into the calculus machinery, and calculus will actually know what to do with. Most of the main theorems with calculus say, assume the function is continuous on an interval, then we can say x, y, and z about the function. And of course, all of the examples that we studied on day 1 of this class were continuous functions. Okay, you could draw all of these without lifting up your pen, and that's kind of the informal grade school definition of continuity, is just that you could draw the graph of the function without picking up your pencil. So all of these are continuous. This function is not continuous, but you can guess where the 3 points where it's not continuous. It's continuous everywhere except for here, here, and here. And that's because we have a hole at x equals -3, we have a hole with a jump at x equals -1, and we have a jump at x equals 1. Okay? So since this function is continuous everywhere except for those 3 points, we can still apply calculus to this function on this interval, on this interval, on that interval, and on that interval. So most functions that we study in this class, they're going to be continuous everywhere. Some of them will have a few discontinuities, places where they're not continuous, but for the most part, calculus applies to every function we're going to study in this class, and they're going to be called a set of continuous functions. Okay, so thank you for your time. I hope it didn't take too much time, and I hope it's motivated what we're going to study throughout the rest of this section. Again, if you get lost in the notation, think of Mario running along a curve.